Okay, good afternoon, guys. So this is what we're going to study today. All right, so you guys remember we studied simple harmonic oscillators last time. You attached a mass to a spring and you saw it oscillate. A mass attached to a spring oscillated like that in simple harmonic motion. Today, we're studying a whole bunch of simple harmonic oscillators in choreograph. So each particle is executing simple harmonic motion, and you have a bunch of them. Okay? And this is what we are studying. Okay, so we are studying wave motion. We are studying waves. Well, let's see what's happening in a way. Okay, so here's an oscillator. What this is doing is this is the medium, and it's pumping energy into the medium. Okay, so it's like you go to a lake and you hit your hand on the lake like that. You're pumping energy into the lake. What's happening to that energy?
Moving outwards.
Yes, so the wave is carrying energy of it. Okay, so you see a wave is a disturbance in this medium that is carrying energy of it. So you can obviously see that this wave is traveling to the right. Okay? Is the medium traveling? You see all those particles? So the medium is not traveling. It's a disturbance that travels when a wave travels through a medium. Okay? And all waves carry energy. Okay? Now, one of the things we'll study is, okay, so let me freeze that. That dotted line is the undisturbed position of the string. When the wave was traveling, so there's a snapshot of the string. Okay, so you can see that that's the undisturbed position of the string, and now this length is longer. So think of a rubber band. Its length has increased. It's been stretched. So there's potential energy. Yep. And there's kinetic energy. Yep. All right. Now, the behavior of this guy, okay, let's, okay, so the behavior of this guy, we would want to mathematically model this. Okay. And when we write mathematical models, what is it generally?
Equation.
An equation. What kind of equation is it?
Function of position.
I'm sorry?
Function of position of the
Right. Well, that's what, yeah, we want to know its function as a function of position and time, but that function, yeah, that is generally a differential equation. Okay? And so we'll look at that differential equation as well. And you'll you'll see that it will never leave you if you're an engineer. Okay? All right. So waves is what we're studying. Okay? And okay, so we'll come to the differential equation and stuff like that. Okay. So we'll talk about two kinds of waves, transverse and longitudinal waves. Here are some of the wave parameters that will define wavelength, frequency, and the speed of the wave. Yeah. You saw that all waves carry energy. Okay, and so we'll give you the equation for energy. We'll show you the wave equation. That is the mathematical model, or that's the equation that string obeys, that vibrating medium obeys. Okay? And we'll talk about strings and then superposition and interference. Okay, so what is superposition and interference? So when sound is a wave, when multiple people talk, or when you have multiple beams of light, or I hit on this end of the lake and Alex hits on this end of the lake, you generate two waves, okay? And how do the waves interfere when they get to the same location, okay? So we'll talk about them. Standing waves, what do you think those are? This is a traveling wave, okay? This wave is traveling to the right. What is a standing wave?
Something that doesn't move.
This is something that's standing, as the name suggests. Okay, and the reason we'll talk about that is, why is this happening? Okay, the reason we'll talk about that is in most instruments, what you do is you pluck a guitar string, for instance, it travels, and then this wave gets reflected from this end. And when two identical waves travel in opposite direction in a medium, you'll get what is called a standing wave. Okay? So you generate standing waves in all instruments. So we'll talk about that. See, here's a standing wave because it's not traveling. Okay? And what happened was a wave traveled to the right. Why is the Okay, so this is a standing wave that was a result of a wave traveling to the right and an identical wave traveling to the left. Yep. Mm-hmm.
It's like the crankshaft for the car.
I'm sorry?
It's like the crankshaft for the car, how we use in the pistons.
Uh-huh. Yeah. Mm-hmm. All right. So we will talk about, we'll talk about some properties that are common to all waves. So mechanical waves are waves that travel in a medium. Okay. So these water waves are a mechanical wave. These are mechanical waves, and so on. Sound waves are mechanical waves. Sound waves, okay, they need a medium to travel through. Electromagnetic waves are waves that can travel through vacuum. Okay? And as the name suggests, those are waves that contain both electric and magnetic fields. Okay? And that you'll learn about in physics too. Here's a different type of wave, something called matter waves. Okay? And these are related to the probability. Okay, so it's a wave function associated with matter, and they're associated with probability. So they're a different kind of wave. Okay, and if we have time at the end, I'll show you a video. Okay, that I want you guys to watch. All right. So general features of wave: when the wave travels through a medium, matter is not transported. Okay, only the disturbance travels. And what is transported?
Energy.
Energy is transported. All waves carry energy. Okay. How can you prove that waves carry energy? Can you give me an example?
Sunlight?
Hmm?
The sunlight, the wave from the light.
Yeah, so you go stand outside in the sunlight, electromagnetic wave reaches you, and you feel the warmth when you absorb it. You can have a boat anchored on a lake. You drop a rock at this end of the lake, and as the wave travels, the wave will lift the boat up and down. Okay? And you need energy to do that. Okay, transverse waves. Transverse waves are the following. Okay, so Okay, so in the transverse wave, okay, the wave is traveling to the right, and each particle is oscillating in a direction perpendicular to the direction of wave travel. That is a transverse wave. Okay. If the particles oscillate parallel to the direction of travel, those are longitudinal waves. Okay. So a transverse wave is when the particles of the medium oscillate perpendicular to the direction of travel. Okay. So the particles are oscillating like this, and the wave velocity is in that direction. Okay, so here are longitudinal waves. Okay, so here's sound waves being generated. So here's in sound waves in air. So you take a diaphragm and the diaphragm oscillates. Okay, so this oscillator is pumping energy into the medium. Okay, and you see it's creating regions of high pressure and low pressure. High pressure, low pressure. So this is a sound wave. And if you could watch a molecule of air, you see the molecule of air is oscillating back and forth like that, in parallel to the direction of wave travel. That's a longitudinal wave. Okay. So here is a sound wave in air, which is a longitudinal wave. A sound wave with can travel in a solid medium. In a solid medium, it can be both transverse and longitudinal. Okay. So what happens is in a fluid, fluids cannot withstand shearing stress, so you can't have transverse waves in fluids. In fluids, you can only have longitudinal waves. In solids, you can have both transverse and longitudinal waves. Okay. All right, here's a more complex wave. When a wave travels in water, okay, the surface molecules go in a circle. Okay, so when this wave travels, the surface molecules travel in a circle. And you saw that in the last chapter, a circular wave is a combination of two simple harmonic motions, one in this direction and one in this direction. So a circular wave is a combination of a transverse wave and a longitudinal wave. Okay? All right, so now we'll talk about some wave parameters. Okay? So the amplitude of the wave is the maximum displacement from the undisturbed position. Okay? So the amplitude is related to how much energy is being carried. So for instance, when I raised my voice, what did I do? I increased the amplitude. Okay? All right. What is the wavelength? The wavelength is crest to crest distance. All right, so for instance, in light, the wavelength, among visible light, wavelength is related to the color that you perceive and stuff like that. Okay? Now, here's an important property of the wavelength. And you guys know ultrasonic sensors. We use them in the lab as well. So you can use any wave to see stuff. Okay? Now, if you are using a probe that has that wavelength, okay, you can see only objects about this big or bigger than that. Okay, so if this is the probe that you're using to see, you can see only the smallest object you can see is roughly the size of the wavelength. Okay, you cannot see this object. You guys understand? Okay. So for instance, your visible light, the wavelength for visible light is between 400 to 700 nanometers. Okay. And the size of an atom is about 0.1 nanometer. So you can't use visible light to see an atom. Do you guys understand that? The smallest thing you can see using visible light is about 5,000 atoms. Okay? To see an atom, what is it that you need then? So an atom is 0.1 nanometer. You would need a light whose wavelength is about 1.1 nanometer. And those are X-rays. Okay? All right, so that's a neat fact to remember. So whatever probe you use, okay, the smallest thing you can see with that probe is roughly the size of the wavelength. You can, of course, see bigger things with it. You know. Okay. Period. Okay, so you saw that each of those particles is oscillating back and forth like that. This is one oscillation, and period is the time for one oscillation. Okay. It also is, if you're standing here, period is also the time for one wavelength to pass you. Okay. So frequency is how many times the particle will oscillate in 1 second. Or it also tells you, if you're standing there, how many wavelengths will pass you in 1 second. Okay? And frequency and period are inversely related. All right, so you saw we generated this wave on the string. There was an oscillator that was pumping energy into the medium, and that energy was being carried away. Okay. Now, in a second, you'll see the usefulness of this. We'll define something called wave number. It's just 2 pi divided by lambda. Okay. And you can think of this as in this length, how many waves are there. Okay. Angular frequency is 2 pi times f, the frequency of the wave. Okay. So angular frequency is also 2 pi divided by t. Okay. All right, now we're ready to tackle the mathematics of it. Okay. All right, so let me okay, let's say I have a function f of x. Now, let's say I want to shift this to the right by a distance d. How do I do that? Yep, this is fx minus d. Now let's do a little more ambitious stuff. instead of making a shift, what I want is, I want it to travel at velocity v.
F of x minus vt.
There you go, very good. F of x minus vt. This is a distance, okay? So in 1 second, it'll have shifted v meters, in 2 seconds, 2v, and so on. Okay? All right, so remember that. So now you learned how to make it travel to the right. And how would you make it travel to the left? Yep, so f of x plus t, vt. All right, now let's do the next step. Okay, so here's a sine function. There's the wavelength. Okay, how would I write this function? So this would be y of x. Y of x is equal to a sine 2 pi by lambda times x. Let's make sure that this is correct. For x equal to 0, this is sine 0. Sine 0 is 0. Okay. For x equal to, so there is lambda, and this is lambda by 2, this is lambda by 4. So for x equal to lambda by 4, that would be lambda by 4. That would become pi by 2. Sine pi by 2 is 1. A. Right? All right. At this position, this is half lambda. X equal to lambda by 2. This becomes pi. Sine of pi is 0. Okay. So you see that this function, it correctly gives you this graph. Okay. All right. Now you can see why we define k. So there is k. Okay. Because this shows up often, so we'll write this as sine kx. Okay. All right, so we've learned how to write that. So you've learned how to write this guy. Okay. Now make him travel to the right. Okay. How do you make him travel to the right? Hmm?
Minus vt.
What minus vt?
Kx minus
So it would be, so you want to make him travel to the right. So it would be, now it becomes a function a sine kx minus vt. Okay. So there is a sine wave traveling to the right. Okay. All right. Now, so you will learn that v, the velocity of the wave, is frequency times lambda. So your function is a sine kx minus vt. V is frequency times lambda times t. Okay. So a sine kx minus k times f lambda t. But k is, so k f lambda is, k is 2 pi by lambda. F lambda, this lambda cancels, 2 pi f is omega. So this is equal to a sine kx minus omega t. So there is that sine wave traveling to the right, whose wavelength is lambda, and whose frequency is f, and whose velocity is frequency times lambda. Okay, so you learned how to write a sine wave traveling to the right for any frequency and wavelength. Okay. Do you guys understand that? And if I wanted to write a wave to the traveling to the left, what would it be? Yep. So here's a wave traveling to the left. Okay. All right. So we've seen this. So here's a sine wave traveling to the right. This guy has the wavelength in it. This guy has the frequency in it. Okay. All right. So this guy is called the phase of the wave. Okay. So for instance, so here's how you think about it. So if this guy was represented by a sine wave, this would be the angle and that would be the value of the function. So that would be the phase. That's the phase, the argument of the sine. And as the wave travels, what you want is, as t increases, this has to increase to keep this constant. And that gives you the constant phase, tells you the velocity of the wave. Okay? So there is the phase, and we want it to be constant. What points are such that as t increases, what point x is such that this phase is maintained constant? And now you take the derivative of this. K is constant, dx by dt minus omega equal to 0. Dx by dt is the velocity of the wave. And the velocity of the wave is omega by k, which is equal to f times lambda. Okay. So for all waves, the velocity of the wave is frequency times the wavelength. Okay. And it's also equal to angular frequency divided by k. Okay. So this is important, and you want to remember this. For how long?
For the rest of your life if you're an engineer.
Yep, for the rest of your life if you're an engineer, and for the rest of your life even if you're not an engineer. Okay. All right. Okay, what is this fella? Wave traveling to the left. Okay. All right, let me show you something. Okay, so you can see that this wave is traveling to the right. Okay, what I'm going to do is I'm going to increase the tension in the string. Okay, so think of a rubber band, and now I pulled harder on the rubber band, and now I'm going to send the wave. Or you can think of a guitar, and what did I do? Increase the tension in the string. Okay, and let's see what happens. Yep. All right, do you guys, can you tell what happened? All right, so you saw that. Okay, what happened now? What was the difference besides the wavelength? Okay, when the tension decreases, the wave velocity decreased. Okay, higher the tension, higher the wave velocity. Okay, so the wave velocity in a string depends on the tension like this. Okay, So it's square root of the tension divided by the mass per unit length. Heavier the string, for the same tension, heavier the string, lower the velocity. Okay, so the velocity depends on the tension and mass per unit length, like so. Okay, so I can, so velocity is frequency times lambda. The lambda sort of is related to the length of a guitar string. So for instance, we'll take a guitar. It's related to the length of the guitar string, so all the strings are the same. And let's say if you have the same tension in all the strings, the heavier string will have lower velocity and will play a lower pitch. Okay, so that's what's happening. You guys understand? Yeah. All right. So here's a snapshot of the string. The wave is traveling to the right. Each element is undergoing simple harmonic motion. Okay. Now, if you look at the snapshot, okay, so think of this as a rubber band. When you stretch a rubber band, it has potential energy. Okay. So you can see that this part is not stretched at all. And this part is stretched the most. That was the unstretched position. And this part is stretched that much. So this has the greatest potential energy, okay? And this has zero potential energy, okay? So here, when the string as a whole has potential energy and kinetic energy because it's vibrating, and each element can be thought of as simple harmonic motion, okay? And now as the wave travels to the right, energy is being carried away, okay? So now the question is, let's say I'm going to stand here, and how much energy passes me per second is the question. That tells you power, okay? So why would that be relevant? Why would I need to know that? See, if that much energy is going, that tells me how much energy I got to keep pumping in to maintain that wave, okay? So that's going to tell you your cost, okay? It's like if you figure out the power for a radio station, that tells you how much electricity bill what your electricity bill will be. Okay. All right. So the average power. So on a string, if you're standing there, the amount of energy passing you per second is 1/2. Mu is the mass per unit length for the string. V is the velocity of the wave. Omega is the angular frequency, omega square amplitude square. So the power depends on the frequency and the amplitude. Okay? And that's what I was saying. When you raise your voice, you increase the amplitude, you increase the power being transmitted. Okay? You guys understanding this? Gabe?
Is it experiencing the most potential energy and kinetic
I'm sorry?
at the equilibrium point? Because every point is going through simple harmonic motion.
This. Okay, so
No,
this.
no, not the peak at the equilibrium point, like this B section. Is that's potential energy because it's stretching, but isn't it also the most kinetic energy because of movement?
Yeah.
So it's both. It's maximum of both.
Right.
Okay.
Yeah.
Thank you.
Yeah. All right. So here's the wave equation. Okay. So what we are saying is, okay, you disturb this guy. Okay, so why is this displacement that you're measuring? Why is the displacement from the equilibrium point? Okay, so let me increase the amplitude. Okay, so here is the equilibrium position. Y is this distance, and x is that distance. Okay, So here's y as a function of y as a function of x. Okay, and that is also changing. This y as a function of x changes with time. Okay, so let me draw this. So here's the undisturbed position of the string, and here's a snapshot. This is x, this is y as a function of x, and t, because as the wave travels, this distance changes. Okay, so there's the string vibrating. And this configuration of the string obeys this differential equation. We haven't derived it, okay? So we are just giving it to you. It's del square, del x square. How many of you know partial derivatives? How many of you don't know partial derivatives? Okay, you don't know partial derivatives. You know derivatives.
Yeah.
You know partial derivatives. Okay, here. All right, so f x y z equal to x square y cube z4. What is this? This is a function of x, y, and z. Okay, it's 3 variables. All right, so you understand that x, y, and z, for every point, you can evaluate the value of the function. So for instance, x equal to 1, y equal to 1. So f of 1, 1, 1 is what? 1. Okay? F of 1, or I'll do 2, 1, 1 is what?
4.
4. And so on. So you guys all understand that. Okay. So I can evaluate this. Now you can ask the question. How does the function change if I travel along the x-axis? That is given by del f by del x. Okay, how does the function change when you travel along the x-axis? Okay, and so this is the partial derivative of f with respect to x. And when you take the partial derivative, you treat the other variables as constants. So what is del f by del x? Treat the other variables as constant. What is derivative of x squared?
That is 2x.
Yep, there you go. 2x y cube z to the power 4. Okay. What is del f by del y? What is the meaning of this? How does f change as you're moving along the y direction? Okay. Oh, hang on a second. It's Gabe's turn. He can do it.
X squared, 3y squared, z to the 4th.
Okay. Del f by del z. So how is f changing as you move toward in the z direction? So for unit motion in the z direction, how does f change? Okay, my friend.
X squared y cubed 4z cubed.
Okay, so now you are experts at partial derivatives. Okay. All right, so here is the wave equation. This is very neat. Okay, so you guys understand that this is the string. The displacement is a function of x and time, right? Because as time changes, this distance changes. And if you change only x, the distance y is changing. This guy, okay, for strings, it satisfies this differential equation. V is the velocity of the wave. I'm giving you this without deriving it, but this is the wave equation. All right, let's look at this. We'll notice a couple of things. Okay, so y, what is the unit for y? That was a displacement, so let's say meters. Divided by x square. X was meters, so meters divided by meters square.
Mention this.
meters divided by meter square, so 1 over meter.
Sorry.
Yeah. So this is an equation. It doesn't matter, whatever the dimensions of this, you gotta have the dimensions of that. There. So there's y. Here's t squared. That's what the velocity is doing. Velocity times t is distance. So velocity squared times t squared. Okay, so dimensionally that's correct. All right, what else is this saying? So this is a spatial derivative. Del y by del x. It's telling you how y is changing with x. Okay? And that is being related to how y is changing with time at the given location. How this will change with time is related to how it's changing with x. Very neat. You guys see that? I mean, these are independent parameters. Okay, so this wave equation is relating how y will change with time versus how it will change with the spatial coordinate. Okay? So anyway, so this is the wave equation. And this guy is describing the behavior of this guy. Okay, I can do all kinds of crazy things to it. Okay, increase the frequency, and all those motions are satisfying that differential equation. Okay, and that was the neat thing. Okay, so since you guys are all experts, what are you learning to do? Here's your system. You want to mathematically model the behavior of the system. Okay? And what was that mathematical model? What you're saying is this configuration of this system, the string, satisfies this differential equation. Okay? No matter where you hit the string, and Alex could be hitting it at one end, and Dalton can be hitting it on the other end. Okay? And no matter what kind of vibration you set up on that string, that guy has to satisfy this differential equation. Okay? All right. Solutions of this differential equation have this form. There are waves traveling to the right or to the left, where v is the velocity of the wave. Okay? All right, so let me show you. And so that equation was without damping. Okay? So we don't want to deal with damping yet.
Do you have to hit the pulse button?
Hmm?
You have to hit the green button to send a pulse?
Okay. Okay, is this satisfied by the differential equation? Does this motion satisfy the differential equation? Yes, it does. Okay? Anything this string does, that differential equation satisfies. Okay? All right. So you see the power of that guy. The behavior of the system is described by this differential equation. And you solve this differential equation and you get, so all the solutions of this differential equation are the various motions that string can execute. Okay? So that's the idea. All right, so that was most of the heavy lifting. Now we'll do some of the fun stuff. Okay? I want to continue the lecture because I'm recording and I don't want to interrupt. Okay? I know some of you guys are tired, but hey, we'll go through this. Garrett, you okay?
Yeah.
Okay. Okay, now what we are interested in is the following. See, what we'll do is we'll send multiple waves in the same medium and we'll see how they will interact. Well, will they destroy each other or what? Okay, so here's a sequence of images. Okay, this pulse is traveling to the right, this pulse is traveling to the left. When they got at the same location, you see, they added up, and look what happened. After they interacted, they retained their shape, and they pass each other as if they've never met. Okay. So waves will add or interfere when at the same location, but they do not change each other's nature. Okay, once they pass, they have their same amplitude. Do you guys see that? Okay. So that's the superposition principle. When they are at the same location, they just add. Okay, and once they pass each other, they're unaltered. Okay. So interference is how they combine. Okay. This is what's called constructive interference when the resultant is bigger than either one of them. Okay. So interference is the phenomenon of waves in the same region of space combining to produce a resultant wave. Okay. Here. Okay. So you can see that two waves combine and then they move on without altering. Okay, so constructive interference occurs when amplitude of the resultant pulse is greater than either individual pulse. So the resultant pulse is greater than either one of them. That's constructive interference. Okay. We will be more often interested in stuff like this. Okay. So okay, so here are two oscillators hitting a ripple tank. Okay, and you see that those are regions of constructive interference. Those are regions of destructive interference. Two waves are canceling each other. Why would you be interested in something like this? So this is a performance hall. These are two speakers, a stereo speaker, and this is where you want to put the most expensive seats. See, you don't want any destructive interference. So when you do acoustic designs for performance halls, you would have to look into all of this. Okay, so for instance, if you have two speakers that are 180 degrees out of phase, then the center aisle is where all the destructive interference happens. Okay, if they are in phase, the center aisle will have constructive interference. Okay, so that's the kind of stuff you want to do with. Okay, did you guys understand that? So destructive interference occurs when amplitude of the resultant pulse is less than the larger pulse. So when you have two pulses of opposite signs, when they combine, you can see the resultant pulse is smaller than the biggest pulse. Okay, so you have destructive interference going on. We will be often interested in complete destruction. Okay, and you guys might remember that from the interferometers that we saw for gravitational waves. Okay. Okay, so what is this? So what are we doing here? Here is a wave traveling to the right. What is this guy?
A wave
Also,
traveling to the right with some phase shift.
very good, my friend, very good. The wavelength and the frequency are the same. So we are going to interfere waves of the same frequency and wavelength, okay? We're not going to interfere different colors. So right now we'll keep things simple. So we are going to interfere two waves of the same wavelength, and also the amplitudes are the same, okay? So here's the meaning of phi. If phi is 0, they're both at this, there's no phase difference, and they'll just combine, and here's the resultant wave. Okay. Now, if phi is pi, here's one wave, here's the other wave, you have complete destructive interference. Okay. All right, so I'm going to pull up a example that you saw. So you use the phenomenon of interference when you want to measure very small distances. Okay. So remember when we measured gravitational waves, the first successful measurement was in 2015, and the Earth-Sun distance, as the wave passed, the Earth-Sun distance increased by the width of an atom. Yeah, let me state that again. The Earth-Sun distance increased by width of an atom. How do you measure such changes? This is interference is what you do, okay? So what you do is you set up your instrument. This is 4 kilometers, roughly from here to the beach. No, from here to US 1. That's how that long that is. Okay, so this beam, you have one beam coming from there and one beam coming from here. And you set it up such that they cancel, the two beams cancels. So when they reach the detector, one beam is reaching like that, the other beam is reaching like this. And they're canceling each other. And the idea was, so if no gravitational wave passes by, this is completely dark. Okay. If a gravitational wave passes by, this length stretches, and so what will happen is now this wave, one of the waves will reach like that. There's not complete cancellation happening. Okay? And you'll see some light. So whenever you want to see slight, small distances, you use what is called an interferometer. Okay. Did you guys understand this? Okay, so the length increased by a small amount, and light was, you could see light. Okay, well, how much did this change? Okay, so let me give you the numbers on that one. The peak strain was 10 to the minus 21 meter, 21. What that means is, okay, 1 meter, that's the fraction by which the distance changed. And so what was this? This was 4 kilometers long. So I'll say it's 10 kilometers long, 10 to the power of 4 meters, 10 to the power of 4 meters. And that length changed by 10 to the minus times 10 to the minus 17 meters. So as a gravitational wave passed, this length became 10 to the minus 17 meters. 10 to the minus 17 meters is roughly the size of a proton. So let me state this again. The distance from here to Beach Street, as the gravitational wave passed, that distance increased by the width of a proton. And there was light there. So that's interference. Okay. Think about this one, the greatest experiment to date. Okay. All right. So we understand that? Okay, so the initial setup is one wave reaches like that and the other wave reaches like this, and you have complete cancellation. Okay? And if there is a slight motion of one or the other, there will be light. Okay? So this is showing you how two waves traveling in the same direction combine. Okay? Now, you see, you can add this, you can, addition and how to add trigonometric functions, but it can get messy. So you've added these two and that's what you got. Okay. So here's the new amplitude. And again, the resultant wave is also traveling to the right. Okay. But here's the amplitude. And when phi is pi, cosine pi by 2 is 0. Okay. And you have complete destruction. All right, so when phi is pi, the amplitude of the resultant wave is 0. All right, so let's say I'm sending two waves, and this fellow here hears nothing. These two waves, tones, completely destructed his location. So how does he tell the difference between no sound or two waves destructively interfering? How do you tell the difference? Change your position. Okay, so if you move, and if he still hears nothing, there was no sound. Okay. So interference is redistributing the energy. Okay, wherever there's corresponding to a destructive interference, there's a constructive interference. Okay. Yeah. All right, so adding these trigonometric functions, so let's say this is two waves, you're adding two waves. If you wanted to add more than two waves and so on, then it can get messy. So here's a little trick. These phasors are a little trick to add when you want to add multiple waves. Okay. Now, again, we are adding waves of the same wavelength and frequency. Okay. What you do is the following. So I want you guys to notice the following. So here's a vector A, theta. What is the y component of this vector?
A sine theta.
Very good, A sine theta. Okay, so you see this guy, you think of this as the vector, that's the length of the vector, and there's theta. So this guy, this wave is, you can think of as the y component of this vector. Okay, well, now let's watch this. As t increases, what is happening to theta?
It's decreasing.
It's decreasing. Okay, so as t increases, theta is decreasing. So you can think of this vector as rotating clockwise. And what is the value of the wave at a given point in time? It's just the y component of that vector. So that's the phasor. Okay, so the phasor is this vector. It's rotating at angular speed omega t. Okay, and the y component is the vector. So let's say you want to add a whole bunch of them. Again, but we're going to only add kx minus omega t and so on. Okay. What you do is, here's the trick you do. Okay. You take that phasor. Okay. If you so you take one phasor, second phasor. Here's the sum of them. And how many can you add? As many as you want. Okay. So you add them. There's the phase difference between each one of them. And here's the net phasor. Here's the sum of all of them. And that is rotating at angular speed omega clockwise. Okay, so this is a trick for adding multiple waves. Okay, so just keep that in your mind. If you when you do circuits, this technique is also useful when you come to AC circuits. Okay. You've seen those cars that drive by and they appear different colors as you see them from different angles. Do you guys know what's going on there? Okay, so here's what's going on. Okay, what is this? What is this? Hmm? I'm sorry?
Oil and water.
Yeah, so oil and water. So here's what's going on. So when it rains, and you have a thin film of water, oh no, so when it rains there's H2O, and then oil leaks, and this is oil. Okay. So here's what's happening. A beam reflects like that, and another beam reflects like this. Okay, so if this light reaches you both with crest and crest, that's, you can see that color. That's constructive interference. Okay, and if you look at it from this angle, and this beam reaches you with a trough, and this beam reaches with your crest, this is destructive interference. So from this angle, you can't see this color. From this angle, you can see this color. So those cars that you see that change color, now they've come up with a technology to put a coating of plastic that has even thickness. And that's what they've done. So they put a coating of even thickness, and depending on what angle you see different colors. Yep. So peacocks, have you seen their feathers? Very colorful. They're not colored. This is what's happening. Okay, so what is it? It's a clear plastic matrix with melanin layers. Okay, and light reflects like from different layers, and they're either constructively or destructively interfering. Okay. So you see interference phenomenon everywhere, and that's what's happening here, there, and so on. Okay. All right. So one of the things that you will be interested in is, so for instance, so reflection of a fixed end. If you send a pulse down on the string, and if the end is fixed, you see a positive pulse becomes a negative pulse on reflection. Okay. So for instance, this sort of mimics the following. If this is a piece of glass, if you send air and glass, if you send a pulse like this, upon reflection from glass, this pulse will become negative as it's traveling like that. Okay. And so they put anti-reflecting coating on your glasses, they use this kind of phenomenon. You have to know this kind of behavior. Okay. And if you have a free end, when a positive pulse goes upon reflection, it remains positive. Okay, so if the end is free. So for instance, from air to glass, the pulse flips, and this is mimicking the following. So from glass to air, okay, if you send a positive pulse like this, upon reflection, it remains positive. Okay. All right, so let me show you standing waves. Okay, so this is showing you here's a wave that's not traveling, and this one that's combining with that, and there is the resultant wave. Okay. So what we're interested in is two sine waves traveling in opposite direction. They create a standing wave. Okay. So here are two waves traveling in opposite direction. Okay. So for instance, if you pluck a guitar string, a wave will travel to the right, get reflected at the fret, and an identical wave will travel to the left. Okay. So here are two waves traveling in opposite direction in the same medium. And what do? You just combine the two at each location. And here's what you get. Okay. And you see this is not traveling. That's traveling to the right, this is traveling to the left, this is not traveling. Okay. That's a standing wave. Okay. And that's what you set up in instruments. Okay. All right, so when you play the flute, the air column, you set up standing waves in the air column. Yeah. All right. So when two identical waves travel in the opposite direction, a string on a string, for instance, they produce standing waves. So here's a wave traveling to the right. Here's an identical wave traveling to the left. You add the two, and you see the spatial part and the time part are separated. Okay, so this is the amplitude. Each point, that's the amplitude at each point, and it's just simple oscillating simple harmonically. Okay, so it's no longer a traveling wave, but it's a standing wave. Okay. So that's what you do in stringed instruments. So here is a guitar string. For a given length, it can only vibrate in certain modes. Okay, so this guy can vibrate in this mode. This is the natural modes of vibration. Yeah, this frequency, that frequency, that frequency. And they are, so these are harmonics. Okay, so if this is 50 hertz, that's 100 hertz, that's 150 hertz, and so on. Okay. Okay, so the loud frequencies, n is the integer, n is v divided by 2l, l is the length of the string, and it's, of course, v, the velocity on the string, is tension divided by mass per unit length. So the allowed frequencies are integer multiples of this frequency, called the fundamental. So F1 is the fundamental mode. That's the lowest frequency it can vibrate at. And this string can vibrate at the fundamental and the harmonics, integer multiples of the fundamental. So how do you play an instrument like a guitar? It seems like there's not a whole bunch of frequencies you can play. So the way you produce different frequencies are, see, for a given string, you can change its length. When you move your fingers up and down the string, what you're doing is you're changing the length of which you're plucking. And then also you can choose which string to play. There are 6 strings to yours. You can choose to play one of 6 strings. The heavier the string you play, the lower the frequency. Okay, so that's how you produce music, by changing the length of the string, effective length of the string, and the choice of the string you play. All right, so for stringed instruments, frequencies of the normal mode form a harmonic series. That is, they form integer multiples of the smallest frequency, the fundamental frequency. For a drum head, you see the frequencies do not form a harmonic sequence. Here's the lowest frequency. The next one is 1.59 times the lowest frequency, 2.14. So a drum head vibrates differently. Okay. So let me show you how a drum head vibrates. Okay. So there is the fundamental mode. Okay. There's the next mode. And so on. All right, so a circular membrane doesn't, the modes of vibration do not form a harmonic series. Yeah. There's a famous problem. The question is, can you guess the shape of the drum head by listening to the music? Okay. And it turns out that so okay, so it turns out that this drum head and this drum head will produce the same frequency. So you couldn't tell the difference between these guys. All right, so mathematically ideal drums with membranes of these two different shapes, but otherwise identical, would sound the same because the eigenfrequencies are equal. Okay, so the timbal spectral would contain the same overtones. Okay, so so what it is so they have the same what is perimeter. Okay, into shape. So the isospectral, if they produce the same frequencies, all right, so anyway, check that out. Okay. All right, so that ends this lecture.